Hi, everyone. Thank you for joining today's DuraMAT webinar on battery reliability. We're going to give everyone a moment to get logged in, so we'll start in about a minute. So thanks for your patience. Once again, if you're just joining, we're going to give everyone a chance to get logged in. So sit tight. We'll begin in about 30 seconds or so. All right, I think we can go ahead and get started. Once again, welcome everyone. Thank you for joining today's DuraMAT webinar on battery reliability from physics of degradation to lifetime prediction, featuring our guest speaker, Candler Smith at the National Renewable Energy Laboratory. Before we get started, I'm going to go over a few quick housekeeping items. Everyone is going to be muted throughout today's presentation if you're not a speaker. And you also have two options for connecting to audio. You can either listen through your computer or by phone. To change your settings, you can navigate to the bottom left-hand corner of your screen where the mute button is and click the little up arrow next to it and then select speaker and click same as system for connecting to your computer audio, or click switch to phone if you want to connect to your phone audio. Also, if you're having any technical issues, you can message me, the host. My name is Jackie Petrie, and I'll help you figure out any technical difficulties that you might be having. And if you have a question for today's speaker, please feel free to submit those at any point using the Q&A panel. We ask that you specifically send questions through the Q&A so we make sure we capture those and don't miss any questions that might come through. And we'll answer as many questions as possible at the end of the webinar. With that, I'm going to hand things over to Laura Shellhouse at NREL to introduce our speaker.
Hey, thanks, Jackie. Happy Monday, everyone. So I'm really excited to introduce Candler Smith, who leads the electrochemical modeling and data science team within the Electrochemical Energy Storage Group here at NREL. His interests are in lifetime prediction of lithium-ion batteries, in developing physics-based models that help accelerate the discovery and design of next-generation batteries for transportation and grid, which is what we're going to hear about today. He holds a PhD from Penn State University and has also co-authored a textbook on large battery system design. So obviously a little bit different than some of the topics we usually talk about in these webinars, but as our community pushes more towards predictive modeling, we realize that the battery community has almost exactly the same challenge that we do. And so we thought this would be a really good way to kind of connect the dots to people and hopefully learn from them and maybe start a conversation. So Candler, with that, feel free to take it away. I'm gonna mute myself and I'll see you at the end.
Okay, thanks. Can you confirm either Jackie or Laura that you can see my screen?
Yep, we do not see you in presentation mode.
Okay. All right, hopefully that's good to go.
Looks great, go ahead.
Okay, all right. Well, thanks both of you for the introduction, for organizing this. And this presentation mostly highlights a lot of work that we've done for Department of Energy, Office of Vehicle Technologies. So that's our primary funding sponsor within my particular group. And we're doing some work with Office of Electricity now, which I'll highlight as well as I go through the talk, but you'll see a lot of vehicle focused types things. And so this dives deeply into the physics of the batteries and how we've gone about modeling that with computer-aided engineering tools. And then the lifetime models, there's still a gap between fully understanding the physics of what's going on, being able to rapidly characterize a cell or a battery system and such. So I'll highlight some of those gaps as well. So I'm going to first kind of give you a really quick overview of what Vehicle Technologies is working on presently. Graphite high voltage nickel manganese cobalt systems are the workhorse of today's EVs. Sometimes you see a little bit of silicon blended in with the graphite. In the future, Vehicle Technologies really wants to reduce cost as well as increase the energy density of these systems. I'm going to start my laser pointer here. In order to tip this cost curve, if you go to higher energy materials, sometimes that helps you get on a steeper cost curve and get to lower costs. But I think that these novel technologies that get to higher energy densities are not things that you're going to be seeing for grid applications. They can only cycle perhaps 500 or 1,000 cycles at the most. Calendar life is very limited for the silicon system. Cycle life is horrible for some of these really advanced systems as well. So you'll be seeing graphite and some different cathode, maybe NMC, maybe LFP and iron phosphate chemistry. But some of the things that Vehicle Technologies Office is active in for even this present material system class is to get rid of the cobalt to make it more recyclable and also enable 10-minute fast charging. So as you look at batteries, depending on who you talk to, whether they're a material scientist or an electrical engineer, they have very different ideas of what a battery is and what are the important research questions and that type of thing. And we've used computer-aided engineering models or CFD type models, very successful to kind of link some of these different length scales. At the atomistic scale, you're looking for new materials discovery, right? What's the next generation material that has higher energy density, higher voltages or lower voltages for the negative electrode. To a certain extent, you can predict some sort of reaction and transport properties that feed up into these continuum scale models. Our group works mostly at the continuum scale, where we predict how the lithium moves around within individual active material particles, the composite electrode, how that contributes to the overall battery's performance. And then as you kind of scale up, the first model that combines together the two different electrodes, the negative and positive electrode, is this pseudo 2D electrochemical model that I'll get into a little bit deeper in a moment here. But it essentially treats lithium transport within the negative electrode particles, the positive electrode particles, and then there's generally a liquid electrolyte that fills up the voids or the pores within this system. There's also a porous membrane separator in between here so that you can transport lithium ions back and forth between the negative and positive electrodes. In perhaps 5 years, maybe we'll have solid state electrolytes, which are viable as well. And then at the cell scale, some of the issues that come up are now things like the distribution of temperature, the distribution of electronic potential, and I'll talk more about that. And then at the system scale, I think you're well aware of a lot of the systems level issues. So I wanted to give you a little bit of history. One of the projects that we initiated, I think back in probably a little bit before 2010, and DOE funded for almost 10 years, is computer-aided engineering of batteries. And this was very successful in putting, filling some gaps in industry tool sets and putting software in the hands of thousands of engineers now that regularly use these tool sets in industry to design large battery systems. So the work that we did early on to kind of help kick off this program and get the auto industry excited about it was to take this macro-homogeneous pseudo 2D electrochemical model where you're essentially treating the complex electrode microstructure as just spherical particles. You're simulating the distribution of concentration of lithium ions within these particles. And then that serves as a submodel for this electrode domain model, where now you also solve for the transport physics in the electrolyte and the composite electrodes. We scaled that yet another length scale further up to the 3D cell domain. Now you've got potential gradients in the current collector foils because you have to carry the current from the tabs or terminals of the cell all the way to the interior where there's a localized region that's producing electrons. And so there's a potential drop as you go from that outside to the inside region. And then also temperature gradients. So there's heat generated within the cell as it's charging and discharging. And of course, you're cooling at the surface. And so there's generally going to be a hotter region in the center of the cell. And that hotter region makes for the kinetics and diffusion processes to be faster. And so you end up preferentially using that part of the cell during charge-discharge processes. And so this isn't an issue when you've got really small cells, but when you really scale up to huge cells, such as in the lithium ion for stationary storage these days. I know there's 250 amp hour LFP cells, and they can have huge temperature gradients if you start to cycle them at above perhaps a C/2 or a 1C rate. So what we did is to treat this jelly roll or the electrode stack as an orthotropic composite with directional properties for the thermal conductivity and electronic conductivity. And with that, you can solve for these performance, some aging questions, and also safety questions. So an example of performance, if you're to design a pouch cell with these different dimensions and either tabs on the same side or tabs on the opposite sides, you can see for one given PHEV type drive profile, the most uniform cell of these designs, this counter tab design, it kind of balances out the thermal and potential heterogeneities. It has only 2.5% difference in the amp hour throughput between different regions of the cell versus the worst case cell has 12.5%. So with those developments, DOE issued a call for proposals for companies to develop software that had similar capabilities but scaled up to the pack-length scale. And several of these companies already had some activities ongoing at the same time that we were developing our models, but we worked together very closely. So these 3 different companies were funded. CD Adapco is now owned by Siemens. EC Power has licensed their tool to GT Suite. ANSYS is still within the ANSYS family. So all these models had great capability to simulate the charge-discharge performance, simulate external flow fields, design thermal management systems and such. Subsequent rounds of KVAT program, we developed parameter identification algorithms, improved the computational efficiency of the models, and then also solved a lot of safety problems. Particularly challenging one was mechanical abuse for crash simulations or crushing of the batteries. So we'd like to reduce the amount of extra structure that has to go around the batteries and still ensure that the batteries are safe in an accident. And then beyond that, our group has been focusing on, for the physics-based models, integrating these models within materials research. So we've kind of delved down a length scale, down to the microstructure length scale, to understand effective properties of the microstructure, how that relates to the tortuosity, which is an important thing that controls the electrolyte transport, which is a limiter for fast charging of batteries. And we've got some open source toolboxes. We've also got closed source simulation tools where we can simulate the complex 3D geometry. Today's lithium-ion systems have only about 5–10% expansion contraction in the materials with charge-discharge processes. Some future materials like silicon have 300% expansion contraction. So we're also presently building in mechanics and large deformation processes into these models. So these 3D models are very effective for simulating safety events and are really good for connecting things that you might run in the laboratory, that type of test data, with a field defect, which might have a different magnitude of short. And I won't go into the details here, but you can get different outcomes, particularly with a shutdown separator. Is a technology where the separator between the 2 electrodes melts and closes off the pores at around 130 degrees Celsius. And depending upon the magnitude of this resistance, which dictates the discharge current, you either heat up the cell very uniformly and the shutdown separator is effective, or you heat up the cell non-uniformly, in which case portions of the cell go into thermal runaway and it propagates. And so these CAE tools or physics-based models are really useful for reducing the amount of experiments that you have to run in the laboratory to prove the safety of a system. Also, safety is when you're abusing a battery, you get very chaotic and you don't get a very repeatable outcome a lot of times when you run safety experiments. So maybe you've got to run 5 test articles to get good confidence in what's going on, how you understand it. And so the physics-based models are very good for providing directional input in terms of, if you change the dimensions of the cell by 10%, what's that going to do for a given test? And then at our lab, we've got quite a range of different characterization tools to characterize the battery electrochemistry and thermal properties to build up these CAE models. So with that, I'll get into the degradation and lifetime topic more. And so I've got a couple slides that kind of give an overview of some of the degradation physics. And then I'll go into an example model where we've gone really deep into detailed modeling of an NMC positive electrode or cathode material particle fracture and how that happens with different state of charge windows and charge rates. But when we go to lifetime prediction, we can't afford to run all these expensive computational models. So the next section that I get to, I'll talk about reduced order models that we use for lifetime prediction. There's still definitely a need to connect the reduced order models with the complex models. So here's one view of degradation, and you can view it in terms of the electrochemical window or state of charge, from 0 state of charge to 100% state of charge. And this is quite dated. Instead of cobalt oxide, say this is NMC or LFP or something like that. You always measure potential with respect to something. And so potential here is measured versus a lithium metal electrode. And so, if you go and measure your positive electrode and your negative electrode versus lithium metal, this is what it looks like. The actual voltage that you see at the cell terminals when you have a complete cell is the difference between these two. So at high state of charge, you've got the highest cell voltage, the biggest difference between the blue line and the purple line. And at low state of charge, you've got the smallest cell voltage, smallest difference between these two lines. And throughout that whole window, you've got side reactions going on. So electrolyte, which is oxidizing, or electrolyte reducing at the negative electrode. And so our observations are calendar life is limited. So these are things that track not with cycling, but just with time. So even if you're not cycling your battery, it's going to be degrading due to these side reactions that are going on inside the cell. And they're always accelerated with higher temperature and generally accelerated with higher state of charge, not all the time. Sometimes they're also accelerated with cycling, and that's because they happen at the surfaces of these electrodes, and the expansion contraction or electrode breathing can generate stresses and cracks at the surface layers and expose some fresh material where there's faster reactions can occur. So then things that track with cycling are typically mechanical expansion contraction related, and these can be accelerated at high or low temperatures and generally high depths of discharge or wide state of charge windows, as well as high C rates. And then there can be other mechanisms that are accelerated just with low temperature or fast charging as well. And so there are physics models of these individual mechanisms, but they're still incomplete. There's additional mechanisms that we don't fully understand. Every different vendor is going to have, some slightly different thing going on in terms of the dominance or prominence of one mechanism or another or something new. And so we can't yet use these complex models to predict lifetime. Another view of this is from this pseudo 2D model. When we talk about fast charging, these are DOE's goals. And presently, if you use a battery with very thin electrodes, you can charge it quickly, and that's because you can get the ions from one electrode to the other very quickly. But it's a higher cost battery, and it's got lower energy density than we would like. And so we're trying to enable fast charging of thick electrode systems. And so the biggest limiters here are carrying the lithium ions from the positive electrode to the negative electrode. And diffusion is one of the processes that carries those lithium ions. When you deplete the ions at the back of this negative electrode here, that means that if the overall battery is charging at a 6C rate, here you're at 0C. There's no charge going on at that part of the electrode sandwich at the back part of the anode. And all of your charge is going in at the front part of the anode. You very quickly overwhelm it, so you saturate the amount of lithium that the graphite can take in, and then the next thing that happens is a lithium plating side reaction to the graphite surface. And then another mechanism is the positive electrode materials or polycrystalline materials, which oftentimes will crack at the crystal boundaries. The way that we're working on building this into physics-based models mainly is with the macro homogeneous pseudo 2D model. And so you can see quite a range of different parameters here. Film thicknesses, loss of lithium inventory and where it went, changes in porosity or active material, which is still available for reaction, effective diffusion lengths of some of these different parameters, surface area. So it's quite a lot of parameters to identify. And this is still a major challenge. So generally when you read literature on physics-based aging models, people assume maybe 3 parameters of changing or 5 parameters, but really there could be quite a bit more. And we still need good methods for novel diagnostics that can drill down and identify precisely which parameters are the ones that are changing. So those are some things that we're working on actively right now. So to go a little bit deeper and give you an idea of one degradation mechanism for a polycrystalline NMC particle, unfortunately, each of these deep dives you want to do, it's basically a PhD dissertation or several PhD dissertations, and the models are too computationally complex to say too much about lifetime, but they can tell you things like effective properties, like the effective diffusivity of a cathode particle that might go into this macro homogeneous model. And so this model is has the kinetics and transport, diffusivity. It's got the mechanics, stiffness and expansion. And then we are using a continuous damage formulation where if you go past beyond a certain equivalent strain, that fracture begins, and this damage parameter goes from 0 to 1. And as it does so, we're attacking or penalizing the stiffness of the material as well as the diffusivity of the material. So it's one way of treating some of the things that we observe in the actual material systems, and say something about, say, a Gen 1 architecture versus a next generation material, which, say, another national lab is developing right now. So it does give you good directional ability. So this is kind of a view of what this polycrystalline particle might look like. The displacement's amplified by a factor of 10. And you can see the individual grains, they can expand and contract in different directions because they're anisotropic. And we've got fracture or damage that's occurring in between them. And I think beyond that, I'll probably just continue on. So now we're getting into reduced order models. So where we really want to say something about lifetime and warranty, for example. And so we've developed a AI enabled tool, which helps a little bit with this process of fitting these models. And then I'll say a few things about connecting it deeper with the physics. So this slide I already covered. Okay, so here's I want to talk through how we've injected machine learning into this process. So this is what actual fade data might look like. This is for an iron phosphate or LFP cell. This is calendar aging only, but you can envision cycle aging conditions might look something like this too. Oftentimes you'll see things with a graceful fade trajectory. Square root of time is a typical diffusion controlled process trajectory. And that's what most of these cases look like. And so when we're fitting models, we can fit it with local models. And hopefully this isn't too small to read, but the simplest one here is relative capacity is equal to 1 minus some rate, beta 1, times the square root of time. Or a slightly more complicated model is to let that power of 1/2 vary. So it's not just square root of time, but maybe it's time to the 0.6. You could make that 0.6 or whatever the exponent is. You can make it a function of operating condition as well. So, you know, maybe if we see at different temperatures and states of charge that exponent varies, we could let that vary. And so it's pretty easy in your fitting code to just try out 15 different models pretty quickly. Of course, you get more and more parameters as you go to these more and more higher order models. But then the next step, which oftentimes would take us quite a bit of time, is to come up with models that would describe how things change with operating condition or with storage condition. And so, for example, calendar aging is a function of temperature as well as state of charge. And the way that the literature says that varies typically is with an Arrhenius equation, which is the exponential of 1 over temperature, times a Toffel equation, which is the exponential of the anode equilibrium potential divided by temperature. But in practice, things don't vary exactly like that. And so in an actual data set, people put in all kinds of fudge factors and try to, you know, do things to help the model better fit the data, as well as hopefully better extrapolate to untested conditions and still give you a reasonable behavior. So what we did, Paul Gasper specifically, and my team, is to use a symbolic regression algorithm, a SISO algorithm, where you feed it features, which are combinations of temperature and anode equilibrium potential, could be state of charge or whatever you'd like to give to the algorithm. And it'll build up equation sets, which I think this one's probably 5th order here, but oftentimes we can get a large data set to be fit with just like a 2nd order equation. And then as we're selecting the models, we'll use cross-validation. So as you fit with more and more degrees of freedom or more parameters, you get better and better fits. That's this black line, but compared to cross-validation data, at some point you lose fidelity against the cross-validation data. So we're generally picking models that have the best cross-validation mean square error. And then we will also plot these equations and manually inspect them and make sure that they seem to extrapolate to reasonable values. So it's still a bit of a time-consuming process to fit these models, but we've basically reduced the labor from about 1 month of labor to perhaps a couple days. And so what that has done for us is to increase, basically double the predictive accuracy. So here's a look at, from that same paper, 4 different test conditions. The old method was the black lines. And if you compare that to the data, you could also look at this residual error plot. You can see the residual error is much higher, or it's diverging from the data set in this case, compared to the new machine learned model, which is, has much flatter residuals. And then on top of that, we are also predicting uncertainty in the model's predictions using a bootstrap method where we randomly resample the data set hundreds of times, and then run simulations with all those different parameter fit combinations. So all of these functions we have kind of distilled into what we call this AI BAT tool, which is available for license. And it predicts lifetime as a function of time cycles, as well as operating conditions. Does some visualization, the local model fitting or deconvolutes aging modes. Then the machine learning or AI part of it is building up these rate laws, how things change with operating condition. And it includes the uncertainty. And then we are working to automatically couple it with a extrapolation model where you can predict untested duty cycles as well. Here's an example of a published paper which I included. This was together with Denso Corporation, who's an automotive parts supplier out of Japan. And this is an example, to show you what a typical aging test experiment would look like. So here for calendar aging, you vary temperature and state of charge, and there's about, looks like 11 different test conditions. And then for cycling, they're varying temperature, state of charge window, depth of discharge, and also charge rate. And so this is a kind of pretty typical test matrix, I'd say. Sometimes we get away with as few as 15 cells. It's always nice to have more data. This particular data set doesn't have cell-to-cell replicates. That's another nice thing to include, which needs some further work, but at least this gives you kind of an idea of what's a typical test matrix would look like that accelerates most of the mechanisms that would be of interest. And so from this, we fit a model which had less than 0.5% error on the training data sets, and then for unfit conditions, it was about 2% error. The model looks like this, where it's got a square root of time component, a square root of cycles or full equivalent cycles component, and then also break-in mechanism in there. And so this break-in mechanism, oftentimes people don't include this in the literature, but we see that initial capacity can either go up by about 1%, or it can fall very rapidly, depending upon what you're doing in those initial 50 days or perhaps 50 cycles on the cell. And some of that could be attributed to positive electrode, the polycrystalline particles kind of cracking and fresh surface areas created, and that dictates what's going to happen to the battery there on out. And so after that, you can get onto kind of a square root of time type profile where things vary much more smoothly. For this particular battery, as well as some NMCs we've been seeing recently, it's not always monotonic versus state of charge. So this is the fade rate versus state of charge, and it is maximum somewhere around 50% state of charge, and actually goes down as you approach like 80% state of charge, and then back up towards 100%. So it's not always a given that higher state of charge is worse. And then cycling fade, we had quite a few different test conditions which all matched this proxy for stress in the active material particles, probably the positive active material particles, but we can't say conclusively without doing cell teardowns and such. And this is, again, concentration gradients are a diffusion-driven process which tracks versus the square root of charge time. And so if you take the charge rate times the square root of charge time, you could also rewrite this equivalently as depth of discharge times the charge rate, both raised to the 1/2. You can extrapolate this model across quite a few test conditions with that, that dominant trend. And then finally, this model, of course, once you fit this model to simple charge-discharge cycling data, you'd like to extrapolate it to real-world, more complex duty cycles. There are still open questions about validating a model that was fit to simple cycling conditions to complex cycling real-world conditions. And this model is relatively, it was successful within 2% for an untested condition, but like I say, more work's required there. For expressing the model in that form, we put it into a state space form where these 3 different states each have their own state variable equation. And the rates of fade, that would be the K1, K2, K3, M3. These things are all functions of temperature, state of charge, depth of discharge, and charge rate. And so as generally on a day-by-day basis, we will calculate stressors on the cell based on the observed operating condition or duty cycle, and then feed that into these equations to predict the changes in these 3 different states of health. And here's an example of going a little bit deeper. This is for a different chemistry, lithium titanate, lithium manganese oxide chemistry. Lithium titanate is a 0 strain material, so there's pretty much no expansion contraction, and you can get something like 15,000 cycles out of this cell. In fact, it seems like it's dominantly calendar life limited instead of cycle life limited. And so here, Idaho National Lab ran these tests, and they fit, there's a diagnostic method in which one can tease out the loss of lithium inventory, loss of positive electrode, and loss of negative electrode from the system. And so we are able to fit models to each of those three things. And with that, you can reproduce the voltage curves versus state of charge at any given state of life very accurately. So if you're doing slow charge and discharge, then you've got most of the voltage response of the battery predicted. But for higher rates or big pulses, you definitely need to add the physics of what's impacting the rate dependent things like resistance growth or transport properties. So there's kind of two different directions we're working this problem, is from the physics-based models and building in the degradation mechanisms, or from the reduced order models and data sets and building in increasingly complex terms that represent the physics. Okay, and then since this audience is probably really interested in system level life prediction, I'll just say a few words on how we carry these single cell life predictions up to the systems level. And this is also something that needs additional work, I would say. In the literature, most of the literature comes from academia, and they don't have access to large data sets of very big multi-cell systems. So I think to the extent that industry partners can work with academia to provide them such systems or data sets, you'll see a lot more in the literature to this end. So our life prediction model is kind of composed of three different submodels: a thermal network model, electrical circuit submodel to represent the charge discharge behavior of a single cell, and then those two are coupled together with the multi-cell model or life model. So to make all this stuff run quickly enough, we express the thermal model in a thermal network form here. And depending upon what your cell configuration is, you might need to redraw this circuit model here, this heat transfer model. And everything's in series, one cell to its neighboring cell. Perhaps cell 1 to cell N might have some thermal connection, which would need another heat transfer path. So this is something that's a little bit difficult to generalize. And sometimes we end up customizing this for each different condition or each different design of cells. It is something that you could identify with computer-aided engineering tools. And so you can easily re-express this in a state space form, which is really quick to simulate. And then for the cell's current voltage response, we use a 2 RC pair circuit model. You could use an electrochemical model, but the electrochemical models generally run somewhat slow. And a circuit model, for most non-limiting operating conditions, does a reasonable job at current voltage dynamics. And this too is expressed in state space form. It's kind of interesting, this model is linear in its state equation, but the output equation here is nonlinear. And that's mostly due to this open circuit voltage, which varies versus state of charge. And then this is all coupled together with the life model that I showed you previously. We've put this together in a piece of software which is controlled by an Excel spreadsheet to define the aging sequence. And so the aging sequence here, it could be rest for 1 day or rest for 30 days. And then you can define any arbitrary cycle that you'd like to define. In this case, a 1C cycle is a new tab on this Excel spreadsheet, which defines the charge discharge limits and such for the simulation. And so the life model is rerun at each different increment here that you see listed in this spreadsheet. So it's kind of stepping through lifetime on a month by month or later on in the life where things slow down, more like a several month at a time basis. And at each of these points in time, it can give you information about the voltage differences across the pack, as well as the temperature differences and such. We have not done a lot in terms of validating multi-cell models, and that's due to lack of data for us as well. We had an ARPA-E project with Eaton Corporation, which gave us an opportunity to do this, and this was probably 7 years ago or so. And so with this project, we took the cells from a commercial pack that Eaton was producing, ran cell level aging tests across perhaps 20 different aging conditions, And for this hybrid electric vehicle, resistance growth is the dominating end-of-life determiner. And so we fit the model to resistance growth behavior. Resistance is generally noisier than capacity. There's more cell-to-cell variability, so you don't see the same 0.5% or 1% error bounds here. You've got plus or minus 10% error bounds on this model. And then the pack level also had a very similar plus or minus 10% error bound. Looks like it's doing a little bit better than that. But one thing that was nice in building confidence with this model is that the individual cell tests were on simple charge-discharge cycles, whereas the pack level tests here were on realistic vehicle drive profiles. And then also, whereas the cell level tests were at constant temperature, the pack level aging tests, once a month, we would change the chamber temperature to a different ambient temperature to represent a different season of the year. And so, we do have reasonable confidence that all these methods do extrapolate well to real world conditions, but needs further work. Okay, and I assume these slides will be made available publicly, and so feel free to peruse some of these different lifetime tools. Some are from our group. We've got a open source Python set of code that simulates 7 different example cells for which there was public data available. And these are reduced order models. Our reduced order models, we have integrated them in several techno-economic tools. The system advisor model is out of NREL for optimizing the economics and simulating dispatch and control of sites with renewable energy, as well as battery energy storage or other time of use type costs for electricity. Reopt is a tool with similar vein, but formulated as a mixed integer linear program for optimization. So life models are integrated into those. For fitting these models, the reduced order models, we've got a open source version of this AI BAT, which is published together with the paper and reproduces the paper results. And then we do have a more full version, which we have licensed to companies as well. And then in terms of battery physics, there is a large effort out of a few universities in the United States as well as in England to come up with either C++ or Python code to simulate the electrochemistry, the pseudo 2D model that I was talking to you about previously, which could also be simplified slightly as a single particle model. So there's a couple of resources here. And then at the pack and systems level, the tool that I mentioned to you, we call this BLAST, Battery Lifetime Analysis and Simulation Tool Suite. NREL will license that with a fee. There are a few open source things from this PyBAM team, as well as from Technical University of Munich. Okay, and with that, just a few concluding words, and hopefully I'm not too late on time. So I would say lithium-ion lifetime is reasonably established, but there's definitely some gaps in our knowledge. Right now, it takes, I'd say, typically 9 months of test data on some 20 cells in order to get a pretty good lifetime prediction out to 15 years and have some idea how it's going to change with operating condition. So a pathway to make that faster is to connect the degradation physics into physics models, build together those with machine learning and AI. For example, we're using a physics-informed neural network presently to try and identify all the physics-based model parameters, how they change with lifetime in a very rigorous way, as well as novel tests and diagnostics, different ways to interrogate the cell and isolate what the degradation mechanisms are. I think there's still a lot of work that's needed to do that. Some things that are possible but haven't fully been addressed, I'd say, are to predict the heterogeneities that are going on in a large system. So that could be within a single large format cell. Say it's a 250 amp hour LFP cell that's being used for C/4 cycling, but occasionally you'd like to do something at a higher rate. What's the temperature gradient going to be? How's that impact aging? Fully understanding cell-to-cell variability. This is still a difficult thing, which changes quite a bit from manufacturer to manufacturer, as well as operating condition can influence this. Building in all the system level effects. And then finally, having a standard lifetime predictive method, both testing and models, is, to my knowledge, something that's lacking in the community. So I think that would help bring maturity to the lithium-ion community. And then beyond lithium-ion, there's also quite a bit to do in advanced chemistries. And so there's a new program from Office of Electricity called ROVI, Rapid Operational Validation Predictive. The goal is to predict 15-year investment grade performance in less than 1 year of data, answer some questions as to how the warranty or lifetime might change versus use. this team of 6 different national labs is going to be working together with DOE, as well as awardees to this long duration energy storage program, LDES. And so there's going to be an element of this program where LDES awardees have to provide their data to a data hub, and then the national lab team will be processing that. I don't think the public is going to have access to all of this data coming in from the awardees, but there are going to be quite a few open tools and software, and it's our hope that out of this program we will also achieve some level of standardization for lifetime prediction, as well as scale it to advanced flow battery chemistries too. So with that, I'd like to thank our sponsors from Vehicle Technologies Office, as well as Office of Electricity. There's also a number of industry partners that have we've worked with over the years. And so thanks, and I'll take any questions.
Great, thank you. Virtual applause. That was super informative and really interesting, cool chemistry. So I'm going to ask you hopefully a kind of easy question to start, and then we can get into some of the questions that folks put in the Q&A, and others, please remember to throw stuff in there as you have them. So I was interested when we were talking about the calendar versus cycle life aging. Can you talk a little bit more about what that really is, and how to think about that kind of more generally?
Yeah. So this is kind of a mess here. Let's see. All right, that's a little cleaner. So chemical side reactions are things that are going to go on even when the cell's just sitting there on a shelf and not being cycled. And so the way that we run tests on that is to just store cells in environmental chambers at different temperatures and different states of charge. And then once a month, something on that order, perhaps early in life, we might run the reference tests a little bit more frequently. We'll run a reference performance test of full charge and discharge to see how the capacity has changed. And there's both reversible and irreversible capacity losses, and sometimes we'll try to tease apart the differences between those two. But the irreversible ones are, of course, the one that we're most concerned about. So those are side reactions, and then the stuff that varies with cycling is most often mechanical expansion and contraction, which predominantly varies with the state of charge window that you're cycling over. So you can minimize this cycling-driven degradation by narrowing the state of charge window. And for calendar aging, you can minimize generally the calendar fade rate by reducing the state of charge. So that says that if you'd like to get I guess there's a couple rules of thumb that don't always hold up, but say your battery has 2,000 cycles lifetime. For each halving of the state of charge window, so if you reduce your depth of discharge from 100% to 50%, there's like a quadratic improvement in cycle life. So if you cut your state of charge window in half, you'd get from 2,000 cycles up to 8,000 cycles, if that makes sense. So that's one rule of thumb you can use. And then for calendar aging versus cycle aging, typical light duty automotive, I see that perhaps calendar life is about 1/3 of the degradation. Cycle aging is about 2/3 of the degradation. They're generally additive. For a commercial implementation of energy storage, you're cycling every day over a wide range. So in that case, probably cycle degradation is going to be very dominant. But I'd say calendar degradation is still something you need to pay attention to.
And do you find that with these two kind of classes of degradation that you can actually decouple them in this way? In PV, we find a lot of times that one thing starts to happen and then that nucleates the next thing, and you have this kind of sequential degradation that can occur. It sounds a little bit like the chemistry and the mechanical here are separate enough that you can think of those as independent and then just additive. Is that truly how it works, or is it just okay as a simplification step?
Seems okay as a simplification step, but I'd like to see more work there as well. Oftentimes we will run calendar aging tests where you're almost running 0 cycles on the battery, fully accelerated cycling tests where you're running as many cycles as you possibly can in a day. And then if we can afford to, we'll put in a couple mixed aging cases where we're doing maybe 50-50 cycling and rest on the cell, or something that gets a little bit closer to the actual system. And generally the models hold up pretty well with that untested condition. But I've got one industry sponsor right now where it didn't on the first try, and now we're going back and looking at that. So in the literature, it's almost always treated as additive, and it probably generally is, but not, I can't say conclusively.
Okay, it's interesting. So I'm gonna ask you one of the questions from the Q&A here. This is from Anubhav Berkeley. He asks, have you used iterative ML so that the AI tells you what kinds of duty cycles, temperature, state of charge, etc., to collect more data on to best improve the model? And then he goes into a little bit more detail.
Yeah, I see that now. No, we have not done that. It would be really interesting to build in AI into the experimental design process.
Right. And then a question from Andrew Gabor, one of our industry members who are on the phone. What metrology tools are missing that you wish you had?
Yeah, there's so many different length scales of the battery, and the more stuff that we could do operando imaging, measuring chemical species or the changes in the mechanical geometry of the electrodes would be really useful. So for example, we just got a nano CT instrument online in the last year, and my colleague Donald Finnegan is imaging cells where the electrode has, he's imaging electrodes at the beginning of life and then end of life, but then also trying to come up with novel ways to do it partway through life with an operational cell. So if we can make those things operando and in situ, that would be a big help to understanding the coupling between mechanical changes, which drive surface area changes, which is the coupling with these calendar life side reaction things. Let's see, you can always get more information from the cell if you've got a reference electrode in it. Then you can measure the individual changes of the negative electrode versus the positive electrode and see how things are slipping. We can estimate that presently with a really slow discharge and charge on a once per month capacity checkups. We call those reference performance tests. But if you could safely implant a lithium reference electrode inside a commercial cell, it would be a big help towards isolating those mechanisms. But typically we're always doing something invasive whenever we're messing with a really big commercial cell from a vendor. If it's a pouch cell, you can slice it open and maybe get a lithium reference between some layers or on the side. But it's troublesome. You're always doing something invasive. So that would be really useful. And then also for large cells, there's some promising direction where folks can use, I think like electromagnetic imaging to predict the current distribution across the cell. And so that would be really nice to kind of characterize large format cells and see what's changing with those.
Cool. All very interesting stuff. I love all of the in situ operando work. So more of that for sure.
Yeah.
So I'm curious, towards the end, you're talking about the lithium ion work and how right now, with about a year of testing, you can get yourself to kind of 15-year prediction. How much information do you need to know once you change chemistry? So if I want to do, say, like a sodium battery, how much data do you need? Are you building from zero, or are there things that you can learn from some of the models that you already have?
To go from lithium ion to sodium, you're pretty much building from zero. If you were to go from a manufacturer's design version 2 to 2.1, I'd say you could still reuse portions of the model or things that you previously learned, but that's the Achilles heel of these reduced order modeling methods, and that's the reason why we need the physics-based models. So it's an important challenge to tackle.
And then just because I'm curious, when you talk about kind of version 2 from a manufacturer, what type of changes are they making in their materials? Is it a slight chemistry difference? Is it like a physical difference in the way the batteries put together? What is that?
Yeah, I'd say they probably somewhat routinely need to change suppliers or have a diversity of suppliers. So it might be that their LFP is coming from a different supplier, and so they need to validate that, and maybe lifetime changes somewhat for that. But then if they want a cell design that goes from a, I don't know, a EV motorcycle to an EV truck or a heavy duty truck or something, typically then you're changing the electrode thicknesses and loadings, the porosity of the electrodes. Also, you might be changing the electrolyte formulation. That's something that dictates the cell's charge discharge performance, fast charge performance, as well as a lot of these side reaction rates.
Great. Okay, so another question. When you were talking about, I think it was one of the hybrid vehicle examples, you talked about resistance growth being sort of your end of life indicator in that case. So can you talk a little bit about how you determine those end of life indicators that you use to kind of help you assess these models?
Yeah, I didn't include material on some of that now I'm realizing. So capacity fade oftentimes will be fairly benign early in life. Like all of these cases here have very graceful fade and follow kind of a square root of time trajectory until a point where there's an inflection point and things start to fade really rapidly. And so there was a review article one of the folks in our group participated in. I think they came up with 6 or 7 different end-of-life rapid capacity fade mechanisms from the literature. And some of them were relatively observable ahead of time and others were not really. And many of them were coupled with resistance growth. So I think tackling not just capacity changes, but resistance and power changes of the cell are important. And one of the things which gets to Andrew's question about metrology tools, the electrolyte's changing, and it's also in some cases drying out, or it's turning into a gas, and the cell is kind of bubbling up, or turning into a balloon, that type of thing. And we need better ways to interrogate and understand why the electrolyte is breaking down and tracking it. Because as electrolyte dries out or turns to gas or leaks from the cell even is one of those reasons for rapid capacity fade as well as rapid resistance growth.
Great. I've definitely had a few batteries that have puffed up. I had a computer turn into a balloon one time, so not good.
That's right. No, it's not good.
I think you talked about this early in the presentation and maybe I just missed it. Simple question, maybe to end on, what do you define as lifetime in the battery community? What defines kind of end of life? Is it a loss of capacity to a certain amount or a full on just dead, not working anymore?
Yeah, this is something that we should do a better job of in the community. So the rule of thumb that engineers use is 80% remaining capacity. So 20% capacity loss is end of life. So that's what a lot of systems are designed to. Or in some cases, I've heard 70-75% remaining capacity be used as end of life conditions. But that said, people are going to keep using the battery as long as it's functioning. And so you'd like to use it beyond that. And the question is how much further can you use it beyond that? And it varies quite a bit based on the particular battery design and how it's been used. And so it's not an easy thing presently to say when the battery is truly going to become unusable or unsafe. So I guess for my own light duty vehicle, I've got a 2015 Nissan Leaf. So it's getting up there in years, but only 45,000 miles on it. And it's doing great with, I think the thing reports like 90% of its original capacity. Maybe it's got a little bit less than that. And so I'm going to keep driving it until it became unsafe or lost acceleration where I couldn't accelerate safely through an intersection. I think that's my deal. And for a large scale energy storage installation, I think you'd want to keep using it as long as it's not a liability or unsafe. So it's pretty important for us in the future to connect state of safety with state of health and understand the true end of life, not just the 80% remaining capacity.
Yeah, well, that's great. Awesome. I love the example with the car. So I'm going to pause for just a minute and see if anyone has any more questions they want to throw up into the chat. All right. Well, I think we have drilled you appropriately. I found personally this super interesting. I do see a lot of crossover between what you're doing, kind of thinking about physics models, reduced order models, and everything. So hopefully we can keep in touch and continue to hear how things are progressing. For folks on the phone, our webinar next month will be a report out from our Communications and Workforce Development Working Group. So that's going to be something kind of fun and interactive. Candler, you're welcome to join us or send any of your team if you think that these will be interesting in the future. But yeah, stay tuned and we'll have that registration soon. And thank you again for this. I think it was super interesting.
You're welcome. Yeah,
Okay.
thanks for everyone's attention and interest.
Great. Everyone have a great Monday.
Bye-bye.